Thank you. As Alex mentioned, I'm Tim Baldridge. I work with Cognitect, and it's interesting doing a talk for the con chair. You get to submit your proposals pretty far in advance. So I submitted the proposal for this talk about 6 months ago, before we even wrote Core.Async. And since that time, there's been a lot of good talks by Rich, David Nolan, Howard Lewis Shipp did a video that's online. Those are all great talks, good blog posts. You should go read that, study it. Yeah, good talk. So, in all seriousness, though, today I want to dive a little more into the how we use Core.Async and less into the why. If you have a question like, why would I want this? I'm probably not going to answer that question. I'd be happy to answer it afterwards, but we're just pretty much going to dive in, starting with the primitives at the lowest level of the language, the public API, and just start building some more complex examples on top of that. So to start with, we import Core.Async, as you see above here. And the lowest level primitive, the simplest primitive to get started with is a channel. Now, when we create a channel like this, just with calling chan, we get a unbuffered channel. And a good way to think about this, I think, is a communication point for two logical threads to transfer a piece of information. And without a buffer like this, it acts as a synchronization primitive. So we can attach a callback onto this channel with take. So we're going to call take on C, handing it a callback. And our callback is just going to print any value that it gets from take. Now, as you see, we don't have any other output. It just returns nil, and our callback is now on this channel. So the callback's sitting there waiting for something to happen. And if we go on to the other end of the channel and put in the number 42, we get nil back from the put on the right hand, and on the other side, we get 42. Now, there's something kind of fun with nREPL here. That's why I have both these windows up, because some things with threads and stuff mess up the way it likes to print out stuff. So I have two windows. But what happens is that when this value is put in by the put, the callback that we attached here at the take is dispatched on a thread pool internally at Core.Async. And we can do this in reverse order. So if we put in hello world, the put is just pending until we attach a callback. Now, there's a couple of things we can recognize about this, and the semantics of working with a channel are pretty clear here. One callback gets one value, and then that callback's thrown away. In the same way, a put is a single put operation, and once somebody takes that value, the put operation is thrown away. So when we instantiated actually you don't see it here, but if we were to just output C, if we just create a plain old channel like this, you'll see that this is called a many-to-many channel down here. So you can have many puts into the channel, many takes from the channel, but they're all synced up one at a time. It's not a broadcast or anything like that. So we can also go in and attach a callback on the put. That says once this value succeeds, once somebody on the other end of the channel has taken our value, we want to execute this callback. So this time we're going to print out done putting when the put succeeds, and when we do take, we see done putting on the one side and got hello world on the other. Okay, so that's cool. We can work with these channels with callbacks. It's kind of asynchronous actions. That's all nice and cool, but now we're in callback hell. We are in the same situation that we would be in ClojureScript. In JavaScript, with a lot of asynchronous operations if you do a web request or something like that. It'd be nice if we could turn this into something that looks a little bit more like normal Clojure code. So let's define a function called take_p, the p standing for promise. And we're going to create a promise internally, and we're going to call take on our channel that we get as an argument. And all we're going to do is when we get a value through this callback, we're going to deliver the promise and put that value into the promise. And then down here, we're going to deref it. So because this callback gets executed on a separate thread, we can block the thread that we're currently executing on, waiting for another thread to deliver the promise, and then we can continue on. So we'll send that over. And now we can do something like spin off a future and just call print line taking from C. And when we put a value in, it works. So now we don't have to worry about callbacks at all. We've turned it from callback code into non-callback code. And we can do the opposite with a put. So same sort of thing. We wait for the promise to be delivered, and now we can have two futures that work just like we expected. Well, it just so happens that this is exactly the way that Core.Async implements its blocking put and take. If you go into the Core async CLJ code in the Core.Async library, it looks pretty close to this. And so these are two common operations, put and take. So they look a little bit weird. But what this means is I like to start with this one. Here we go. So this is called take blocking. And the arrow kind of goes in the direction that the data is going to go. So we're pulling out of the channel into the next S expression. And the first exclamation mark kind of means that it's not transaction safe. We're doing a kind of a IO operation. If you did this in a loop inside of a swap or inside of a transaction, it doesn't interact with the transactions. You're going to do multiple takes, so be aware of that. And the second one just signifies that this is a blocking operation. The second exclamation mark says, you know what, we're using promises. So whatever thread you call this on is just going to sit there and do nothing until you get a value. And then the inverse of that is the put. So put and take works just like we'd expect. Now, there's a problem here, and that future returns a promise, and you can see that down here. It returns this core future call blah pending. And that doesn't really fit in well with the rest of Core.Async. We're dealing a lot with channels. We like to work with channels. Let's make future return a channel. So that's exactly what the thread macro does in Core.Async. It works just like future, if you've ever used future, except the thing returned from this is not a promise that will be delivered the value after the body is evaluated, but it's a channel. So if we execute thread, we get a many-to-many channel once again, and we can take from that channel and get the value. So thread executes, it sticks the value 42 in the channel, and then we can read from it from the other side. Now we can nest these arbitrarily. We can put a take from a channel inside another channel, or inside another thread block, and it works as expected. So this is all well and good, but every time now that we start one of these threads, we are running in an actual OS thread. And the nice thing about our original design that we had with callbacks that we saw at the beginning of this talk is that they're just callbacks attached to a channel. It's all memory-based. The channel goes away. The callback gets discarded. That's kind of nice. It's all running on this thread pool, a fixed-size thread pool behind the scenes. It would be nice if we could have really lightweight logical threads that look like normal threads, but they act internally, they're being rewritten to attach themselves to channels. And that's exactly what the Go block does. So interface looks a lot the same. Instead of thread, it's Go. So here, if we do Go 42, it returns a many-to-many channel. We can take from that, and we can nest them arbitrarily. Now, what's the deal? Why do we only have one exclamation mark? Well, if you remember, the implementation of the double exclamation mark version, the blocking take, uses a promise. And so if we were to use that version of the function, this thread pool, this fixed size thread pool behind the scenes is going to block one of the threads that's going to sit there, and it's going to be tied up until someone delivers the value. And that kind of gets around the whole purpose of writing this Go block in the first place. So instead, we differentiate between parking take and blocking take. And this right here should be an exclamation mark, not a question mark. So parking take says, take the rest of the body of this Go, turn it into a callback, into a function, and attach it to a channel. That is a really complex macro that is a pain to write, but it's written now, so don't worry about it. What we basically do is we take the body of the Go and turn it into a state machine and then jump around between the different states of your code. So it looks like normal Clojure code, but it does weird things internally. So this is what the internals of Go 42 looks like. And I'm not going to walk through a lot of this today. And something as simple as this turns into code like this. Now, don't be scared about this. It's basically a lot of auto-gen symbols that look weird. And in the end, the JIT gets a hold of this and turns it into something that's actually pretty fast. Some tests I've done have said you get about a 50% slowdown for code just inside the Go, which is pretty good. It was about the target of what I was looking for when I wrote it. But the key is that any of the code inside this Go block is going to be turned into callbacks that are attached to these channels, but the semantics that you expect from Clojure still hold. You can do try blocks, catches, loops, any of that sort of loop recur, all that stuff just works as expected. You can even do really weird stuff like taking from a channel inside the catch or the finally block. So if you throw an exception, you can do an asynchronous operation in a finally block, and then once you're done, the exception continues to propagate. Okay, so that's Go blocks. And if you're interested in any more about that, you can go on YouTube and type in Core.Async internals, and I have about 2.5 hours where I walk through the macro and stuff, if you're interested in that sort of thing. If not, don't worry about it. All right, so thus far we've been talking about unbuffered channels. We can also provide a parameter to a channel, in this case an integer, and if we pass an integer to the channel, it's going to create a buffered channel of that size. So in this case, we create a channel, a fixed length buffer of size 1. So what's going to happen is the first value we put in, it'll say, are there any takers to this channel? Any takers on the remote end? No, there's not. Do we have a buffer? Well, yes, we do. Then let's put the value into the buffer. And so this put succeeds instantaneously. Even though we don't have any takes, we have a buffer, the value goes right into the buffer. Our second put into this channel does not succeed because the buffer is now full and the next put is trying to put in, but it doesn't have anywhere to go, so it parks the Go block on the channel. Once we take one value from the channel, the second put continues and goes in and it goes on its merry way, and then we can take the second value out and we get our values 1 and 2. So this is what we call back pressure. And this is kind of a nice feature, is that with these fixed length buffers, there we go, we can allow a Go block to run a little bit of ahead, a producer to run a little bit ahead of producing values for the consumer, but yet if it ever gets backed up where the consumer is just completely incapable of consuming at a certain rate, then the producer will also block and we're not doing needless work. Now there's two other types of buffers that we can use that we can pass directly to channel. A dropping buffer is the first one. And this says, now when the buffer is full, just start throwing away any new values put into the buffer. So we can create a dropping buffer channel, put the first value, put the second value. Now these are called unblocking buffers. There is no way these buffers or these channels can ever block for puts. So as we see here, both of our puts succeed instantaneously. And then when we can only take one value from this channel, but when we take from it, we get the value 1. The second value was just completely thrown away because the buffer was full and the buffer dropped the value. Sliding buffer is the same thing, but it drops from the other end of the buffer. So it's a sliding window over the values put into the channel. When we create that the same way, both puts succeed, and when we take from the channel, we get 2. Because the first put was thrown away when the second put succeeded. We also have a concept of close, and this will be important in a little bit, so I'm going to cover it real quick. If we create a channel and close it, and then take from the channel, we get nil. You can't put nil into a channel. This is one of the reasons. But nil is kind of a signal. When you get nil from a channel, it's a signal that the channel is closed, and you can exit whatever loop you're currently working in. And that'll be important in just a second. All right, so this is all cool, but sometimes you want to take from multiple channels at a time. You may be waiting for multiple asynchronous responses and you just want to get the first one and do something with it. So we're going to create 2 channels, A and B, and put something into A, and then alt. So if we think about this, A has a value, B does not. But we can alt on A and B, and what we get back is the number 42 and the channel that we got it from. And that would allow us to make some decisions about perhaps where we got the value from would decide some logic farther down. So because B didn't have a value, this operation doesn't block, it just took the value from A and continued. If we did this the opposite way and put it into B, it would still succeed just fine. So we can create a channel called a timeout. And a timeout channel is kind of a special case of channel. But what it does is we give it a time in milliseconds, and after that amount of time, it closes. And when we close a channel, it returns nil. And so based upon that and alts that we showed just above, we can create a take with a timeout. So what this says is take from A doesn't have a value, so that'll block forever, or from timeout. And after 1 millisecond, timeout will close and the block will succeed. And there we go. So that's a good way, for instance, if we did an asynchronous web request, we could say, wait for this asynchronous web request to succeed, unless 10 seconds pass, in which case there's probably something wrong and we're just going to fail and continue on. We can also do alts with writes, or any combination thereof. So here we are doing a put into A, but there's no takers, so that'll block, or timeout after 1 millisecond. And that works as expected as well. Alts also has a couple options. We can have a default. If we provide a default to an alt, it'll always succeed, but only if there are no values to take from any of the channels. So here we're saying take from A, or return nothing found if we can't take anything from A. So this allows us to do a sort of non-blocking take. Now what's interesting about alts, and this is kind of a really cool feature of Core.Async, and if you go into the channel implementation that Rich wrote, you'll see that there's a lot of really weird locking code and ordering of locks, and that's the part I'm glad I didn't have to write. And Rich did that, thank you. So what's interesting there is these alts are canceling. So when we say to 3 different channels at once, I want to take the first value from any of these channels, we apply a callback to each one with a cancellation token, basically. And when one of those succeeds, you can atomically cancel the other takes or the other puts. And that's one of the, I would say, one of the hardest parts of Core.Async to understand if you were going to dig into the internals. But in reality, we don't run into that much. Just understand that something like alt here, where we're taking from, or we're putting into A, or taking from the timeout, only one of those will ever succeed. Now, the order of operations on an alt is undefined. It's a random ordering. In fact, we actually have a random number generator that tries taking from A and B in a random order. And the reason for this is that if we always did them in the same order, you could starve some channels and other channels would become full and your system could have undefined properties. So we have sort of a randomness in there that helps write programs that are easier to understand. And we can see that here. If we put, let's see, 3 A's into channel A, 3 B's into channel B, and take, there's some alternation going on between which order they're taking from. And that's completely random, unless you provide priority true, in which case they happen in the order they are defined. Okay, so that's cool. What can we build with this sort of thing? That's pretty dry, abstract stuff. So a problem I often run into when debugging code that's multi-threaded is I get this situation where 5 threads print to the screen at the same time, and I get this mismatch of code on my screen that's half of one line and half of the other. So here's one way perhaps to solve that. I like to call this single-threaded access to a shared resource. Is kind of, I haven't found a better term for it yet. But we could create a channel called logging channel, and we spin up a thread. And all it's going to do is loop, and it's going to take from this channel, and if it gets nil, then this when let will fail and we just print out log closed and we're done. Otherwise, we print the value that we got. So we have this thread out there waiting to take from this channel and it's blocked. And if we close that channel, we see our log is closed. So let's create that again. And we're going to create this function called log. And log is just going to send the message to the log channel. And now we can call log a bunch of times and the other thread is printing out the data. And what's nice about this is that if any number of threads can be calling put on log, or it can be calling this log function, and the messages are serialized in output. And yet we can ignore normal parallel code, which is cool. And this is a more complex example that I'm not really going to go into. So let me back up real quick. The code that we see here today, I'm going to upload onto GitHub shortly after the talk here. I got about 1,000 lines of examples like this, and we're not going to cover everything. But I hope to perhaps these are going to be things that anyone can walk through, get kind of a feel for Core.Async, play around with it, say I like this, don't like this, whatever. So here's a little more complex example. And this is like a thread pool. So we handed a channel and a function to execute on every value from that channel and say, here's how many threads we want to spin up to be processing values from this channel. And if those threads are idle for a certain amount of time, shut them down. And it's actually not that bad amount of code. All right, so let's do something a little more useful though. Let's interface with HTTP-Kit. Someone asked this last night at the end session, hey, how do we interface with asynchronous libraries? So HTTP-Kit has this really nice feature where you can make an asynchronous HTTP call that's handled by a single thread somewhere. And when the response completes, the HTTP response completes, it's going to call a callback. All right? Well, this is pretty easy to do. We'll just require it. And we're going to find this function called HTTP-Get that creates a channel. We're going to print out the URL for debug purposes. And then we're going to get the URL, and our callback is just going to throw the response into the channel. And now other people can block on that. Go blocks can take from that. We can alt on multiple responses, do a whole bunch of things with it. So we're going to define an API key here. Today I'm going to be querying from the movie database. So we're going to get some information about movies. Yay. All right, so all we have to do, so top-rated movies here just calls request and process, which is going to do an HTTP GET, take from the channel. It's going to grab the body from the response, and then it's going to use Cheshire to parse the JSON and return a Clojure data structure that we can do things with. So we have this function, top-rated movies, which just kind of wraps up the URL nice for us. And there we go. So this is an asynchronous response. Another thread is going off and doing the actual web request and handing us back a channel, and we're blocking on that channel until the response completes. So we're just going to define a couple other things here. We can query by cast, query by peoples, like get information about individual actors, and we have this average function. All right, so here is a fun little function I wrote. It says, for a given movie, make a request about the cast of that movie, and then take from the channel that we return. Now go into the data that we got out of that channel and find a sequence of all of the cast members. So now we have a seq of maps. And we're going to use core map, Clojure core map, to grab the ID of each one of the cast members. And then we're going to call people by ID on each one of those cast members. Each people by ID function returns a channel. Now we're going to use this function called async map. What async map says is given a function and a sequence of channels, we're going to take one item from each one of the channels and apply the function to all of them, in this case vector, and then it returns you a channel that you can take those values from one at a time. So what this is doing is this map people by ID will return us a sequence of channels. This turns it into a channel of sequences of people. We take from that, then we go in and grab the popularity of everyone and average it out. And what you'll see here is we'll see the initial request for the cast of the movie, and then maybe about 20 requests for all the cast members getting their individual info. So here it is querying all the different people. We got 20 requests or so running, depending on the speed of there we go. So the average popularity of the people in the movie The Godfather is about 1.572. Yay, all right. But we can see a little more clear example of what this allows us to do here. So let's say we need to contact 10 different URLs. Here we're going to do the same URL 10 times, but it'd be about the same. So we really want to know information about Ben Affleck, because he's an awesome actor and all that. And he's Batman. All right. So we're going to take this 10 times and we're going to time it. And normally some caching kicks in after a while and we get a little bit, okay, so about 5 seconds. Now we're going to do something different. We're going to initiate all the requests at once, but only take from them after we've started them all. So it's more of a parallel or concurrent doing 10 requests at once. And it's about 88 milliseconds. And we can even run that again because caching kicks in, but it's on average about 5 to 10 times faster. So this is what's kind of cool, is that by changing around where you do the takes from the channels and how you wait on certain things, you can often get better, you can trade off some memory and connections, some extra TCP connections up at one time for faster response times. Okay, so there's another construct implemented recently called mult. Remember I said that it's a single put only gets delivered to a single take. Mult kind of mixes that up a bit. We're going to define a channel, and we are going to create a mult that looks at that channel. And what we can do now is with a mult, we can attach channels to it that are subscribers to every single value. So anything given to mult is going to be broadcast to every one of the tabs. And those tabs can be added and removed at runtime. So what this loop here does is it creates a channel, taps the mult with the channel, and then goes into a loop, and it's the same loop we saw before. Run until you get a nil and then exit. So we can create a couple of these. And if we put in 42, we see all 4 of our waiters get it. And once again, and when we close, we see all 4 of them exit. Now we close the top level channel. And this is why, because the reason for this is that a lot of Core.Async primitives are based on this idea of of kind of like a tree of channels. And when you close the first channel, it'll close its children. And there's options to say, no, don't close your children. But in general, this is the default behavior you want. So in this case, closing to mult will close that channel. And then mult will say, the channel closed, I will exit. Now I go into all my taps, all the subscribers, and close all of them individually. And then once that happens, all the Go blocks shut down as well, and everything just kind of cleans up. So that's kind of an interesting pattern to think about in your code is can you define it? I mean, there's a couple ways you could do this. You could have another channel passed into this block and alt off of both of them and have like a closed channel, and when the closed channel is closed, everything shuts down that way. But the other option is just to do it this way and kind of express your program as trees of channels and processes. Pub/sub is a bit like mult plus multi-methods. So there's a function here. I probably won't go too much into this example, but this function that we pass in called, it's a keyword tag in this case, is applied to every message, and that applies a topic to every input of the pub/sub. And then subscribers can subscribe to one or more of the topics at a time. And we're getting a little low on time, so I won't go into this. So this is kind of like a fake version of Twitter where you have hashtags attached to messages. This is about dogs or cats, and people can listen to certain topics and only care about those. This is actors, and we won't go into that. I have a limited critique of kind of the differences between Core.Async and actors. But the one thing I want to talk about in regards to a lot of this is that people have asked me sometimes, so how does this differ from actors? How is this better than actors? That's not the thing I think we need to be so much concerned about as to think about what is the right paradigm for what I am doing right now. This is something Rich mentioned last night in the unsession, and I think it's very good. And that is, I see it more of a problem when your language limits you to a certain paradigm. I don't necessarily want to program in a language where all I have is Core.Async, or all I have are raw threads, or all I have are actors. I think the best features of Clojure is that we can use atoms, or we can do a swap on an atom inside of a Go block. That we can have things like reducers that are high performance parallel operations on Clojure collections. That doesn't work so well when you try to do that with CSP, which is what this is with Core.Async, which is a form of CSP. So I would say more, think about it in that way, is that what are the trade-offs of a certain paradigm, and should I be using that in my program? Okay, so I want to come down here. Okay, so we talked about before, all of these Go blocks are based off of a code transform that turns into a callback that's attached to a channel, which sounds an awful lot like the way things run in JavaScript, which is pretty true. So there isn't any technical reason why we can't port a lot of what we just saw to ClojureScript. So I'm going to start up a browser REPL here and switch over and reload this. There we go. And so we're going to require the ClojureScript version of Core.Async. And we can do JS alert. Hey, all right, our REPL is now running in a browser. And we'll just do what we did before, have a channel. Works, great. We can put onto it, attach a callback, that works. Can we create a Go block? All right, yes. And sure enough, here's the JavaScript code for take. So one of the first things when I worked on this I got thinking about was, you know what, this sounds a lot like green threads, which is like a whole bunch of processes and callbacks that you can kind of pause one logical thread and jump to another logical thread and jump to another one. And I wanted to try something like we're about to see. This is close to something David Nolan did, but I had the idea too, so. So we're gonna attach our canvas object on our HTML page and define a whole bunch of colors. And we're gonna do this thing called make cell. So we're gonna pass in an X position and a Y position to this cell, and it's going to loop forever. And it's going to set its rectangle to a random color. It's going to fill that rectangle with a color, and then it's going to wait on a timeout for a random amount of time. And you can see this loop never exits. It's just a loop that runs forever. But at this take, what happens in the Go block is that it's kind of going to unwrap the loop. So if we have a round loop, it's going to stop here at the take, unwrap it, and attach the whole thing as a callback on the channel. So we can do that, spin up 10,000 of them. And here we go, 10,000 individual processes running in a browser at a time. And what I think is interesting about that is we can start to think of things in a little bit different ways. I remember doing some animation in JavaScript at a dark time in my life. And a lot of it was dealt with attaching callbacks onto set timeout, and then you had to keep some state and do all this other stuff, where now animations could just be a Go block that waits for a certain amount of time, sets the element color a little bit more to a different color, and continues. And that's kind of cool. So if that's all the case, can we port our movie database query to this? Yeah, and it looks pretty close to the same. Obviously, our interop has to change. So now we're going to call the Google Clojure with an S function xhirio send. I don't know what that acronym stands for. And we're going to just say, okay, we get our response back, we get the data we got back, get the response as JSON, and convert the JSON to Clojure, and then put that into a channel. So this operates a lot like we were the other function we were looking at with HTTP kit. And our key, and request and process that does some URL concatenation, and top-rated movies. Now here in this Go block, it's interesting to note that in the other version we use the double exclamation mark, the blocking take that uses the promises. We don't have that in ClojureScript because a blocking take from a channel is pretty much impossible. You have one thread, you take a blocking take off of something, and there's no way you can ever succeed. So all of these operations with the put and take exclamation mark like this have to be done inside a Go block. So we're going to spin off a Go block to do this work. All right, and and I haven't mentioned this yet, so I should. Most operations like alts that we were looking at before that have an exclamation mark also have a version that have a double exclamation mark, and you kind of have to just think about where your thread is currently running. If you're running in a Go block, use the one with a single exclamation, use the other in the other case. All right, so there's our web request. We'll define movie ID, so on and so forth. The average, we got our average function. We have to do this thing called getHelper. This is another interop problem. Since we don't have Cheshire, one nice feature of Cheshire in Clojure is that it takes your keywords in JSON and converts them into Clojure keywords, and then you can use them as functions and a whole bunch of other stuff. I didn't take the time to do anything like that in ClojureScript. So we got to work with strings and we got to move some stuff around. But it's pretty much the same thing. Get the movie cast, get the cast sequence out, get the ID of everyone, get every request to everyone's information, turn it into a vector, find the popularity, average it, so on and so forth. And if we run this, we'll see here in our browser, we are making a ton of web requests that are slowly completing, and when we're done, there we go. The same thing again. So I think this is what's pretty cool about Core.Async, is that a lot of the code, except for the interop, and you can make the interop look a little bit nicer here by turning the keywords into Clojure keywords, but a lot of, besides interop, a lot of the code just ports pretty straightforwardly from Clojure to ClojureScript. And I was talking to a coworker recently who was working on something. Actually, come to think of it, it was Pedestal, and I asked him, how was the porting process going from Clojure to ClojureScript? And he's like, I tested it on Clojure and just loaded it in the browser, and it just worked. Well, great. I'm glad it worked for you that time. But the porting process is actually works very well. So that's about all I have for today. That's kind of a brief overview of this. Like I said, there's a lot more code here. I'll upload on GitHub. And if you see me around, feel free to grab me, talk to me about what you like, what you don't like, yell at me because of something I said today or whatever. So thank you. And we got about 3 minutes for questions. So, yes?
Tim, on line 362, you're doing a do C over a set of channels?
Yes.
So this is where you did a bunch of parallel requests, but you're looking for the responses in the order that the requests were created, not the order that they're actually arriving at.
That's correct. Yes, yeah, that's correct.
Is there a similarly succinct idiom for receiving them in the order that they arrive?
That could be done. I don't think I've done that. Normally, the two things I want is either get me the first one. Like in this case, if I'm making 10 requests, I could make one request to 10 servers, and then just fastest wins. I either want that or I want them all, in which case I really don't care in the order that they come in. You could save a little bit of time, right, by processing each one as it comes in. I haven't seen, actually, no, the way to do that would be to wrap each one of these in a, the way to do it would be to have HTTP get take an optional channel. Instead of creating its own, it would take another argument as a channel, and then you just read 20 items off the same channel, and as they complete, they'll put their results in, and you can take them out. Yeah, and that's something common I like to do is have the input channel or the channel that the function will use as a response be a optional parameter. So it'll create its own if it wants to do that, or if you don't provide it one. Otherwise, you can have multiple requests use a single one. So, yeah. Any other questions? Okay, yes.
So I assume then that within a Go block, one should not do any blocking I/O?
That's correct. We chose an arbitrary thread limit of number of CPUs plus 42, because 42 is a cool number. But yeah, the idea is basically give you enough that if you accidentally do some I/O, you might not shoot yourself in the foot, but go I/O all over the place inside a Go block and you're gonna have problems, So, but the thing to mention there is that the thread blocks that we created run in a cache thread pool, which is pretty much, well, unbounded except for by your operating system in size. So if you need to do some I/O, spin up a thread to do it and communicate with it with channels and then do all your CPU heavy work in a Go block. All right, thank you.